Okay, so here's the statement. If a number is a rational number, then the number is an integer. Okay, so the hypothesis, a number is a rational number. Remember, we're not including the if. So, a number is a rational, I promise there's not as much writing on this one as last week. A number is a rational number. Then, the number is an integer. So the conclusion is the number is an integer. Don't include the then. The number. Okay. Is the statement true? If it's a rational number, do you remember rational numbers? So, can you think of a rational number? Could be any fraction or a decimal that's not an integer.
Couldn't a rational number be a whole number too?
It could be.
Okay, so then yeah.
So, but we're saying if it's a rational number, then it has to be an integer.
No. Gotcha.
So, it's kind of the opposite. If it's an integer, it has to be rational, because all the integers are rational numbers, but the opposite is not true. Okay? So, give me a rational number that's not an integer.
0.5.
0.5. Good. So that's our counterexample, and all you need is one to prove the whole thing false. If you can find one example, yep, 3.25. But if you find one example, you're done. Okay? So that's the power of a counterexample. It can prove the whole thing false. So it's actually kind of easier to prove something false than to prove that it's true.
So what about like 4/2? Would that be a rational
4/2 is 2.
Yeah, I know.
So it's a rational, yes, so
even though it's put as a
any
fraction.
whole number or integer is also a rational number, because you
Okay.
can put any number over 1 and make it a fraction.
Okay.
I have a question.
Yeah.
What if there is a conditional statement
Uh-huh.
which works for everything, but there's only one thing which disproves
Yeah.
it and nothing else disproves it?
And you
Would
can't
it-
find that one thing?
Or
Or
you found the
you
one
found
thing.
it, then that works. It's true for everything but one case.
Okay.
Then it's not true.
Oh,
Okay?
it's not.
That if it's not true for one thing, then it's not true. Okay, does that make sense?
Yes.
Okay, so now some more vocabulary. The converse of a conditional statement is when, kind of like what you did, when you interchange
Switch it.
the hypothesis with the conclusion. Okay, so here's another one. If a number is a whole number, so there's your hypothesis, then it is an integer. So the converse would be, if it's an integer, then it's a whole number. Let's look at that. This one's true, this one's not. 1, 2, 3. These are the whole numbers, dot, dot, dot. Okay, and then the integers include these. All right, so if it's an integer, is it necessarily a whole number?
No.
It could be one of these.
So then,
But this one's true, right? Because if it's a whole number, then it's a subset of the integers. If they're both true, then they can be combined. So if these had both been true, they could have been combined into a biconditional statement using if and only if. Okay? So let's look at this one. If b is divisible by 2, okay, to get a whole number, that's what we generally mean by divisible by 2, then b is even.
yeah.
Okay? The converse of that is if b is even, then it is divisible by 2. I think we agree that those are both true. So then the biconditional is b is divisible by 2 if and only if, and I usually abbreviate that, IFF, but you can write if and only if. But IFF is often used by mathematicians to mean if and only if. IFF, b is divisible by 2 if and only if b is even. Here we go. We're going to look at some examples. So we're going to identify the hypothesis and the conclusion and tell whether the statement is true or false. If it's false, we're going to give a counterexample. Okay. If the absolute value of a number is positive, then the number is positive. So what's the hypothesis?
The absolute value of a number is positive.
Exactly. I'm going to do this and with an arrow. You guys can write it. Or you can do what I did if you want. And then the conclusion.
The number is positive.
Okay. And you guys remember what absolute value is. So is this true?
Yeah.
Is it? So if the absolute value of A is greater than 0, then does that mean A is greater than 0?
No.
Because you could have, what's a good
Negative.
counterexample? Yeah, or -1, okay? There's my counterexample. The absolute value of -1 is 1, so it's greater than 0,
Yeah.
but -1 is less than 0. So what is the hypothesis of the statement? If a number is even, then the square root of the number is an even number.
Not true.
So, the hypothesis. And you look at these. Which one's the hypothesis?
A number is an even number.
Right. Okay, which number serves as a counterexample to this statement? The reciprocal of a number is less than the original number. So this is 1/2. The reciprocal of 1/2 is 2, and it's not less than 1/2. So he's right. Good job. It's B. You go. Reflexive, symmetric, and transitive. These three are also true for line segments and angles. Okay? So the reflexive property, A equals A. Okay, so line segment DE is congruent to line segment DE. That seems pretty intuitive. Okay, pretty obvious. Symmetric property, if A equals B, then B equals A. We can see the same thing. If segment DE is congruent to segment FG, then segment FG is congruent to segment DE. Same with angles. These come in handy when we're doing proofs. Okay, transitive property. For algebra, we know if A equals B and B equals C, then A equals C. Same thing for angles and segments. If DE is congruent to FG and FG is congruent to JK, then the first one is congruent to the third one. Segment DE is congruent to segment JK. And it works for angles too. So I listed these out for you because they're going to come in handy when we're doing our proofs. Now, I also gave you a list of postulates and theorems, but these aren't on there. That's why I made a separate list of these. Because when you're doing proofs, you need to have these ready to go. The other thing that's on here is the distributive property, which you guys should know. Okay? So, we're going to use our properties that we've got on that sheet to prove a statement, or writing a reason for each step. So the first one is always easy, and this is going to be true in your geometry proofs. It's given. Okay? What's my reason that I can go from this to this?
We have to distribute the
Distributive property. So we need to cite a property. Perfect. I'm abbreviating. Distributive prop, or distrib prop. Okay, what's the reason I can go from this to this? It's combining like terms or simplifying. Yours would be fine too. That's good. Okay, what's the reason I can go from this to this?
You're trying to get X alone.
Addition property of equality, right? What did you say?
I said you're just trying to get X alone.
Exactly, which is the addition property of equality. EQUALITY. All right, and that's where, if you remember, if in 5th grade you did the hands-on equations with the scale, and you could put things on the scale, and whatever you added to both sides kept it balanced. Did anybody do that? No.
Yes.
Yeah? Yeah, I like that.
I was like, I didn't do that.
Okay, and what about this?
Division
That's
property.
Division property of equality, because we're dividing both sides by the same thing. Okay, so a theorem is a statement that is proved, and we've talked about that before. And we prove theorems using things we already know. So we have the given information. Remember, we put given up there. We have the definitions. Okay, postulates. Remember, those are statements that we can accept without proof. And then we can also use any theorems that have already been proven. So we have all of those things at our disposal to write as our justification for steps in a proof. And for this purpose, we can treat the properties of algebra, so the things on that list, as postulates, so that we can accept them without proof. So this sort of reasoning is called deductive reasoning, kind of like what Sherlock Holmes does. All right. Now, independent reading. There are two theorems, the midpoint theorem and the angle bisector theorem. Make sure you look at them now. And those are theorems, now that they've been proven in the book, that you can use in your proofs. Okay, so we're going to use a form of proof called a two-column proof, and this is going to be a good example of one. You can also write a paragraph proof. You could write out the same reasoning in a paragraph form. But I really like this approach, and the book likes this approach, and this is the approach you're going to see on your tests. Now, a lot of times in your tests, there will be kind of a fill in the blank. So they'll have some of these written, and maybe a couple of these will be blank, and you're filling in the blanks. Sometimes you're going to have to construct the proof from scratch. The good news is, here's what we're given, here's what we're trying to prove. So we're given that angle A is congruent to angle B. This is going to be the transitive property. And that's on your list. We're proving it now. Angle B is congruent to angle C. We're going to prove, given those two things, that angle A is congruent to angle C. So the nice thing is that these two are given. So generally your first reason is always going to be a gimme, an easy one. We're given these two things, and our next step is to say, well, the measure of angle A equals the measure of angle B. How can we get from here to here? Do you remember where we got that in the book?
Well,
This,
we know that angle A and B are equivalent, so then wouldn't the measurements have to be equivalent too?
it's the definition of congruent angles. So we're using a definition here of congruent angles. If the angles are congruent, their measures are equal. Okay? So write this down. Okay. Now, what about number 3? So that would be the same reason, right?
Yeah.
Okay. So I'm just going to put this, okay? On a test, you might want to actually write it out, but, okay. Number 4. So then, the measure of angle A must equal the measure of angle C. How do we know that?
Isn't it transitive?
It's the transitive property from algebra. It's on your sheet, okay? Okay. So then if the measure of angle A is equal to the measure of angle C, then we can say that angle A is congruent to angle C. And what's that reason? This, going from this, says the measure that the angle can't be substituted. We use substitution a lot. It's not quite appropriate here. We're going back to our definition of congruent angles again. Okay?
A plus B and B plus C, so then there's
Yeah, that's the transitive property. That's how we got to from here to here, from these two to here,
Okay.
right? And then this
Well,
is
wouldn't-
just the definition of congruent angles again.
But like,